Hello, my name is Ahmed Merzoug and I am PhD student at the University of Texas at Austin. This work was done with collaboration of my fellow student Leil Liu and under the supervision of Dr. Michael Pyrcz at the University of Texas at Austin as part of the direct consortium. I'll be presenting minimum acceptance criteria for conditioning subsurface models using generative AI. The outline of today starts with an executive summary, an introduction, the methodology, results, and we dive into conclusions with the limitation of this work. Generative artificial intelligence is proposed as a solution to overcome the limitation of traditional geostatistics. So it allows us to condition to data locations and at the same time condition to the geological formative process. However, the application of generative AI need to be checked quantitatively and not qualitatively. So we propose the application of minimum acceptance criteria protocol to augment and establish statistical model checks for robust quantitative checks of generative AI-based realization. We apply the proposed workflow on different algorithms, including variational autoencoder, generative adversarial network, and diffusion probabilistic models. The results showed that each model has an inherent limitation to it, and we need to be cautious when using any of these models in order to avoid any expensive decision-making process that can lead us into losing money. We recommend that this protocol is always applied before the application of any generative AI subsurface modeling techniques in order to put leap of faith in the realization and continue our decision-making process or our investigation processes while we build models for any purpose that we think may be useful for us. So generative AI is a new paradigm where it resulted in new reservoir modeling capabilities that promise the realm of geological realism that can be offered by the rule-based models as we see here on the plot. We can get the maximum of reservoir heterogeneity and at the same time get a limited data conditioning that is offered by the variogram-based approach. So generative AI is basically include the different algorithms, so which one to use and how can we use them. A lot of people until today use visual inspection or limited quantitative checks. So we propose a protocol where we have minimum acceptance checks for subsurface generative AI models. These checks are applied on 3 different algorithms to compare them and see which one perform best to each task. The methodology of this work starts with generating training images. In this case, we use sequential Gaussian simulation. And the reason why we use sequential Gaussian simulation is that we know the truth and we can evaluate all the algorithm against this because we have most of the metrics for the sequential Gaussian simulation. However, the metrics can be extended to other applications. So we generate different sequential Gaussian simulation result realization or simulations for different variogram ranges. Then we train a generative AI model for each variogram range and different generative AI models. We generate realization, then we apply the minimum acceptance criteria checks, and then we report the results. This is for unconditioned realization. However, we run this protocol for conditioned and unconditioned realizations, and I will show you in the next slide how we condition our realizations. So the realization that we have are our conditioned realizations. So the unconditioned realizations are basically unconditioned SZ simulation. Then we take them, we train machine learning models on them, and these models are called unconditioned models. If we take these models and we optimize the latent space in order to replicate certain data observed at specific locations, they called conditioning variational autoencoder, conditional GANs, or conditional models. However, in this case, we only focus on conditional GANs and conditional VAEs, and we did not delve into the conditional DDPM. That may be a research that we do in the future. There are another type of models or realization that we do are preconditioned models, and these are conditioned sequential Gaussian simulation to specific data patterns and data locations. And then we take the machine learning models and we train them on these conditioned models. We named the SG sim realization preconditions in order to ensure consistency and that the user or the person that follow this presentation be able to distinguish all these models from each other. One of the models that we use are variational autoencoders or VAEs. So VAEs is a machine learning model that is composed of an encoder and a decoder. The encoder takes in an image or the training image or the training subsurface models, and then it compresses into a latent space. The decoder takes that latent space and try to reproduce the same image that the encoder took. And with time and training, the machine learning model will be able to reproduce the same image. However, what we do here is basically once the model is trained, we take only the decoder and the latent space, we generate a latent space, and then from that latent space, we generate images through the decoder only. So we separate the decoder on itself, and then we generate images using that. Another model that we use is generative adversarial network or GANs. GANs are composed of two main blocks. We have a generator and the discriminator. The generator takes in a latent space, and then it maps that latent space in order to generate an image. This image along with real images go to the discriminator, and the discriminator try to discriminate and find which image is real and which image is fake. And these two compete. So the discriminator is as a detective, and the generator is like an art forge. So we try to create images that are similar. With time, the generator improve in generating realistic images, whereas the discriminator improve in detecting these images. After we train the models enough, we only take the generator in order to generate the subsurface models, and we use them. The third model that we use is diffusion probabilistic models, and this is the state-of-the-art generative AI models. It is composed of two main processes. The first process is the forward diffusion. In the forward diffusion, we take subsurface models or training image, we add noise to it, and we save that noise. The noise is added according to a schedule, where we add noise incrementally. Then we train a unit in order to denoise the image. So we start from the noise and we try to get to the original image. In the same process that we did the forward diffusion, we try to reverse it and remove noise iteratively. And this way, we start with a random noise in order to generate a new realization. After we train each of these machine learning models, we run the checks for the training images and the generated images. Here we see some generative AI realizations for the different model and sequential Gaussian simulations at different variogram range. The checks that we have are 6: global univariate distribution, local uncertainty, global uncertainty, global spatial continuity, local data exactitude, and dynamic response. First, global univariate distribution. In this check, we check the global univariate distribution using two methods. We have a histogram overlap and we have QQ plot divergence area. For the overlap of histogram, we take 100 realization of the training images generated using SGSIM, and we have generated images generated using generative AI model. So we pick one model for a specific range and we take that. We flatten each distribution, and then we build a histogram for that. Then we compare the different histogram for the training images and the generated images. The overlap is with reference to the training images, so we see how much we are reproducing of the histogram distribution of the training images. Note that we use 100 images in order to avoid any randomness that can be associated with a single realization. For the QQ plot, we plot the generated images and the training images percentile, and then we calculate the divergence area compared to the 45 line. The smaller the area, the better the reproduction is. The larger the area, the worse the reproduction is. Note that through all this work, for each metric, we try to propose a numerical way of evaluating this in order to avoid any visual inspection that can be subjective. Second, local uncertainty. For the local uncertainty, we calculate the expected value of by cell porosity standard deviation. So we generate 100 realization for any generative AI models, and then we calculate the by pixel standard deviation. Then we calculate the expected value for all the realizations after we calculate the by pixel one. We compare this value for training images and any generative AI model. For global uncertainty, we use a dimensionality reduction technique. So one of the reasons why I use dimensionality reduction technique is that images are very high dimensionality data. And in order to compare them at this high dimension, it's a little bit hard. So what we do, we reduce the dimensionality into something that we can see and something that we can measure, and then we run our statistics there. So we use multidimensional scaling, and in order to avoid also any visual inspection, what we do is that we fit two kernels, a kernel for the training images and a kernel for the generated images. And then between the two kernels, we calculate the minimum value, and then we normalize by the kernel density estimator of the training images. That gives us an overlap percentage. And as you see here in the top, a low overlap is basically images that are totally different. And if we see more overlap, it shows that the images are similar and they fall together in the low dimensional space. Fourth, we have spatial continuity reproduction. For the spatial continuity reproduction, we use 2-point statistics where we calculate the experimental variogram, which is a measure of the spatial continuity. Once we calculate that, we calculate it for 100 realization of the training images and 100 realization of the generated images. Once we calculate it for the training images, we calculate an average variogram. Then we average the error of the generated images from the average variogram of the training images. And this is only calculated up to the range that we specified for the training image. And then we normalize to the number of realization that are calculated. This calculates the exactitude of a reproduction. However, for the variety of a reproduction, we calculate a spatial overlap coefficient or a percentage where we calculate the minimum spread of the training images compared to the generated images, and this is always with a reference to the training images in order to ensure that we compare to the training images spatial continuity variety. Fifth, local exactitude. For local exactitude, what we do is either through preconditioning the training images as the SGSIM, where we try to ensure that we have this 5 well spot patterns where we have 4 producer and 1 injector, or through optimizing the latent space, and then we calculate the mean square error and we report the truth plot in order to see how good of a reproduction these models have and if they honor the local data conditioning. Sixth is the dynamic response. In the dynamic response, we start by generating a permeability field, and that's through doing a fine transformation in order to ensure a log normal distribution. And then we run a flow simulation. In the flow simulation, we assume that all producers are producing at 1,500 barrels a day, whereas the injector is injecting at 600 barrels a day. This is a water flooding experiment. And then we calculate the recovery factor. So the recovery factor is basically calculated, the exactitude of reproduction of the recovery factor is calculated using an epsilon p50, which is the relative error of the generated images compared to the training images, normalized by the recovery factor of the training images. In order to know the percentage of error that we are expecting to encounter, we ensure that this value is not an absolute in order to know if the model is under-predicting or over-predicting the recovery factor. Another measure of the variety or the uncertainty in the recovery factor is the overlap. So the overlap is calculated as the spread between the training images and the generated images, so the minimum one, and then we normalize by the time. And we also, since these values are normalized by the training images, it's going to end up as percentage. Now for the results. So the results, we start with the global univariate distribution. So we see that the variational autoencoder models struggle to reproduce the data distribution, especially for preconditioned variational autoencoder on the top right. The unconditional VAE perform a little bit better, and the conditioned VAE perform a little bit similar to unconditioned VAEs, except for the short ranges. So we see that the VAE models improve as the range increases. The GAN models and the DDPM models have a good reproduction, and they were not affected by changing the range. The same thing applies for the QQ plots, divergence area. And we see that the GANs have the best reproduction, followed by the DDPM, and then the VAE models have the least reproduction. Second, for the local uncertainty, we see a little bit of similar patterns. The VAE models struggle to reproduce the local uncertainty or the bipixel expected standard deviation, and they suffer from mode collapse. So the mode collapse is basically where the generative AI always produce the same images, which is going to give you a very low standard deviation. GANs have a very similar reproduction of the local uncertainty compared to sequential Gaussian simulation. And then if we go to the DDPM, we see that the DDPM has more variety and more larger standard deviation. And this is due to the noise adding or subtracting procedure, where it does not always end up in the value bound, and it gives more spread to the data. Third, global uncertainty. For the global uncertainty, talking about the variational autoencoders, we see that unconditional VAE have the best performance compared to the other VAE models. However, all VAE models tend to improve performance with a longer range. We see that for the GANs, unconditioned and conditioned and preconditioned have the best reproduction of images. However, for the conditioned GANs, they have some limitation in the reproduction. However, there is still similarity to the original images and the global uncertainty there. The DDPM are ranked second to GANs with the good reproduction of images, as we see here. And now for the spatial continuity, we see that the VAEs have large error when trying to reproduce variograms, especially for the preconditioned VAEs. The unconditioned VAEs have some error to them, and the conditioned VAEs improve as we increase the range. We see that the GAN models have very low reproduction of variogram error, and the DDPM models has also very low error. However, the GANs has the best performance in the exactitude of reproduction of the variogram. Talking about the uncertainty of the variogram or the variety of the spatial continuity, we see that variational autoencoder have the lowest overlap percentage, and the GANs have the best overlap percentage in terms of a variety of spatial continuity or the uncertainty in the spatial continuity, followed by the DDPM. Talking about conditional GANs have a very wide variety in the uncertainty. Sometimes they have a good performance, sometimes they fail, and this is something that the practitioner need to be aware of while using these models. Fifth, for the local exactitude, we try to see the error, the average error per 100 realizations, and see how far the conditioning to local data is using mean square error. We see that conditioned VAEs have better reproduction at longer range, and the preconditioned VAEs have the lowest error, and this is basically because of mode collapse. They tend to reproduce the same images. Conditional GANs have low error, so they are good in the reproduction. However, preconditioned GAN has a little bit higher error compared to the conditioned GANs. And then the DDPM has a low error, so they tend to reproduce a good local data conditioning. So for the dynamic response, we see on the right how the simulations response is and how good or bad the models are, so we can have an idea about the numbers that we see here on the plot. We see that for the PP50 or the exact reproduction of the recovery factor, preconditioned GAN have the best performance, followed by the DDPM, and then conditional GANs and VAEs have almost similar reproduction. Then the worst are preconditioned VAEs. For the uncertainty, we see that the reproduction models are ranked as preconditioned GANs, then conditioned GANs, and then preconditioned DDPM, followed by conditioned VAEs, and preconditioned VAEs are the worst model. So using preconditioned GANs and conditioned GANs can be safe. However, we need to pay attention into the uncertainty reproduction in terms of preconditioned GANs and conditioned VAEs, because they tend to have very low exactitude or variety. So to conclude, we have developed this table where we compare the different models across different statistics or metrics, and we label them red as very low reproduction, and then orange need to be cautious when using them, and then green is high and can be safe while using the model for this specific task. So the proposed minimum acceptance criteria allow for more quantitative checks of generative AI. We see here the limitations of each models and where we should be cautious while using it. GANs outperforms other models in the majority of tasks. Using VAEs for subsurface modeling can result in a poor decision-making process, as they tend to underestimate the recovery factor and suffer from mode collapse, which can lead to wrong investment decision-making processes. The limitation of this work is that it was developed only for and applied for continuous data only, and the models are compared to SGSIM training images, and only basic architecture are used. So other variants can result in different performance of the systems or the models. And the condition process used constraint optimized by linear approximation, and using other algorithms can result in different results. Basically, by having different latent space, we can expect to have different results. And finally, I would like to acknowledge all the sponsors of the Direct Consortium who have supported our research. And thank you so much for attending this presentation.